everyone, welcome to the next module. Today let's see how do we simulate using multisim the hot wire anemometer. Getting to the details about simulation. So initially let's construct the bridge circuit. So I'll take the 4 arms of the bridge. And then change the resistance. Let's take 150 ohm here. And then the same thing here. Let's assume, okay, we have the platinum resistor here, which is the other arm of the bridge, and here on this end, if I have mentioned in the previous module, we need a higher resistance on the other arm of the bridge. So let's assume we take 1K on 1K. We could even choose a 5K resistance. So it's okay to choose a higher resistance on the other arm of the bridge. Assuming 10K would be sufficient. So this is the resistance that I've chosen on the other arm of the bridge. Now that we have the 4 arms of the bridge, let's connect it to the source. So here we have the source. Let's give a source voltage of 10 volt. Yeah. And then connecting So let's establish connections to all parts of the bridge. Now let's consider the amplifier circuit here and then establish connections from each of this branch to the bridge circuit. So the other terminal goes to the other arm of the bridge, and we have to connect the supply to the amplifier. So as we can choose from the source, let's choose a voltage source here, and then since I need the positive terminal, what I do here is rotate and then establish a connection between the positive terminal to the source. On a similar basis, I choose the other source and then connect it to the amplifier. And here the negative terminal goes to your other end of the amplifier. So here it is 12 volts. That should be fine for us to drive the op amp, and then let's connect a base resistor here. Let's change the value of this base resistor and let's keep it to around 270 ohm. And then having a connection between the base resistor and the output of your amplifier. So the output of the op amp goes to your transistor. So let's choose the NPN type transistor here. That goes from the output of your amplifier I am feeding the output of the amplifier to the transistor. So let's get the source here and then the transistor somewhere here. Let's establish this connection and then let's connect the source voltage to your transistor. And the other end goes to the ground. So I choose the ground icon here and then establish a connection between the other end of the source to the ground. So we have a 10 volt DC source here going as an input to that transistor, and from the transistor to the bridge circuit, and this has to be grounded here, the bridge circuit, and from the two terminals of the amplifier, two terminals of the bridge to the amplifier, and then output of the amplifier driving the transistor. Here let me choose a variable resistor instead of the standard 10 kilo ohm resistor. Here I choose the pot so that I can manipulate and explain to you how the parameters across the bridge can be changed and how it affects the entire setup and how feedback mechanism can be achieved using this circuit. So here we've connected the two sources of the amplifier, but we haven't connected the ground. So let's make the ground connection to the two sources. Yeah, so this basically sums up the entire process of building the anemometer circuitry. So we have the 4 arms, the Wheatstone's bridge circuit, which is given as an input to the amplifier, which drives the transistor here, and then we have the source voltage. This forms a basic circuit for the anemometer. Now let's consider the case study. Assume I have already mentioned you to have a look at the temperature conversion table. So this, if you check, this is, we assume we are using a PT 100, the heater here, and this is the table. If you I am sure you can Google this and then find out the conversion table. So for each temperature, here there is a, for each temperature and resistance relationship is what basically the entire table would tell you, and here this is the different grade. Like you say, it is more like a quality parameter, the quality factor index, where assume for minus 90 degrees Celsius, if you buy a grade 0, then this is the temperature what you get, and if you buy a grade 1, then there is a difference, a minute change in degree based on your standard. Now let's assume we have room temperature which is 30 degrees Celsius. Assume this this is the room temperature at 30 degrees. So what is the resistance at 30 degree PT 100 or can offer here is 111.67, but since I am using a PT 1000 in the arm, the compensation circuit, correspondingly what is mentioned here is I can just multiply it by 10. Assuming at 30 degrees Celsius, the resistance offered is 111.67. So assuming I am building up this circuit and the current temperature of my room is 30 degree. So what is it that I am supposed to set the compensatory circuit at? 11.1. As you can see, this is set at 11. Since this is a variable resistor and then I have used a 10K, I have set it at 11.1%. So essentially it is going to give me that resistance. 11% of 10K is what I am connecting my compensatory circuit here at. Now I am driving the voltage. Now what is it at 30 degrees Celsius? You want this resistance. We are talking about a constant temperature circuit. So you want your device here to be maintained always at 150 degree Celsius. That means the resistance should always be maintained at 150 ohm irrespective of the change in room temperature. It could be an increase in temperature of room, the room temperature could go as high as 40 degrees or it could go as low as 10 degree. However, this part of your bridge should always maintain a constant temperature. How does that happen? You can maintain the constant temperature at 150 only when you are able to control the resistance of this bridge. Now how are you able to control the resistance of this bridge? Because of the feedback mechanism what we have here. Now this is now the case study 1 here. I am talking about room temperature 30 degrees Celsius and I have set the compensatory circuit accordingly. Now what happens? So these are a few voltage and current. You can always monitor at different points of your circuit what is the voltage and current that is being driven throughout your circuit. Now this is the like you can see, this is 5 volts. Now it is ideally, if you assume 5.2 and 5.2, the bridge is almost balanced. Assuming now my room temperature is increasing from 30 degrees Celsius, it rises to 50 degrees Celsius. So what happens? My compensatory circuit has to be, say, let's assume. Now keep a note on the amount of voltage and current here. So here the current that is currently being driven through the circuit is 22 milliamps. And you can see here 157 ohm, because like I mentioned you in the conversion table, ideally at 0 degrees Celsius it has to be 100. And what happens when the temperature increases? So there is different gradation and hence we have considered this resistance here. Now assume I am going to change the compensatory circuit here, assuming the room temperature is increased to 50 degree. So what does my table here tell? At 150 degrees it is around 157.33. Now how do I simulate that condition here? I am going to change this resistance to 157. So that becomes 15%. Yeah, say this is the room temperature which is risen from 30 to 50 degrees. So what happens, can you see there is a large variation in voltage. This was ideally 5.2, but what happens here, there is a drop in voltage. And what happens when I simulate, there is a significant drop in voltage. So this is at 6 volts and this is at 5 volts. Now this is your voltage and current. Setting back the room temperature to 30 degrees Celsius, assuming this is my room temperature. Now there is a less difference in voltage, and this is the current. Now let's say case 2, when airflow is happening through this device of mine. So this is the 150 ohm resistor R2, and then air flows across this. What happens when air flows through this resistance? Ideally the temperature should drop, and what happens when the temperature drops? The resistance drop. So I want to simulate that condition. What happens? Let me reduce this resistance, assuming I am flowing air at some meter per second velocity. And what happens with airflow? My resistance significantly drops. And kindly look into the parameters. Now the resistance is dropping and there is a 10 ohm difference. And what happens? There is a drop in voltage. Now what I want you to look at is what is happening to the current. What should happen? As the resistance keeps dropping, your feedback circuit should work in such a way that it will inflow current, so that self heating happens through the resistor and it regains its normal temperature. That is, it should come back to resistance, so that the temperature is maintained at 157. Now what happens? Assuming there is a lot of airflow and your resistance is dropping. So now keep at 130 ohm load. What is the current? It is 24 milliampere. Assuming there is an increase in airflow, so there is a drop in resistance because there is a drop in temperature, and the current has increased from 24 to 25 milliampere. As you can see, there's a 1 milliampere increase for every change 10 ohm of resistance what I am changing. So from 150 ohm we have come down to 110. So there's 40 ohm difference. And what happens? You see the feedback circuit is pushing more current through this part, so that self heating happens and it regains with the increase in current which is pushed through this, it regains the temperature. So this is the intention behind rigging up this circuit, and you always want your load to be working at constant temperatures. And you see how the difference between the two voltage is always being adjusted by the amplifier here and fed back to your circuit. So this was the brief introduction about how you can simulate an anemometer, the 4 arms of the bridge driving through which are fed to the op-amp and then to your transistor. As your flow, assuming this is an ideal condition, we have used a compensatory circuit at 30 degrees Celsius and the relative resistance are chosen accordingly. Assuming there is some amount of airflow, because of air flow there is a change in the heat flux, that is the amount of temperature across the resistor drops, there is a change in resistance and accordingly you have the drop, and then the feedback mechanism works, drives additional current, self heating happens and the circuit regains its balanced. So, there is some amount of time the feedback circuit takes to bring back the resistance back to the desired condition, so that the temperature across this arm is maintained constant. So, this was about the simulation and how to rig up. Let us see how in real time scenario we can have the anemometer circuit. Let us blow in different temperature air across your load and see how the temperature varies and how your feedback mechanism maintains the temperature around your desired arm at a constant rate. So, this was the simulation part for today. Thank you.